Welcome tonight to our first presentation for 2021, and this was a very timely conversation that Mike and I had at the AGM about Mike's, this was the subject actually of Mike's PhD thesis when he was in New Zealand, and I just had a conversation with him and he said Australia wouldn't fund his PhD, so he had to go to New Zealand to get it funded. And worked with another Australian, which you'll hear about. So across to you, Mike.
And he did his PhD at Hobart.
Oh, there you go. So probably known to a few people.
So it's a bit incestuous in a way. Yeah.
Over to you.
Okay. Good evening, all. This is really a follow-up to the talk I gave back in August 2018 on. You want me to start again? No. In August 2018, called An Introduction to Radio Astronomy. And I know there's been quite a bit of interest in the Decametric Radio Astronomy here in Tasmania, mainly because Groth spent the last half of his life here, believing that was where the interesting work was. And Graham Ellis ran a reasonably active radio astronomy department here in Hobart. And the other real major centre was up in Sydney. The University of New South Wales was extremely active in the 1950s. And as far as I know, I'm the only actual radio astronomer that ever did a PhD in New Zealand.
There you go.
That was almost 50 years ago. Okay, now essentially decametric radio astronomy is radio astronomy with wavelengths of tens of metres. You can't go much below about 5 metres, because 5 megahertz, because the ionosphere just isn't transparent enough, and you get all the shortwave broadcasts jamming you out because you're running pretty broadband receivers. So really the golden rules are you've got to have a source that's within about 45 degrees of the zenith. If you get much below that, you start getting all the long distance HF transmissions, and really it's got to be 4 hours after sunset it takes for the ionosphere to decay, and about 2 hours before sunrise. If the sun's hitting the the top of the atmosphere a couple of 100 kilometres up 1,000 kilometres to the east, then it's just like someone turns a switch on and next minute you're flat with shortwave radio stations, or it used to be back in the 1970s when there were lots of them. It was just like someone turning the light on. And so it's a great thing if you haven't got a life and you want to spend your winter nights up on top of a mountain in an unheated building hoping something might happen. Now, something like radio amateurs. Yep. Now, one of the leading lights in the 1950s. Remember, radio astronomy didn't really start until 1945, because Groth did his work in the late 30s, early 40s, but it was the development of radar and the discovery that the sun actually jammed radars that suddenly come after the war. There were lots of physicists who'd worked in radar was interested in having a look at the sky at these radio wavelengths. There was a whole universe to discover. Well, Alex Shain and Charlie Higgins from the University of New South Wales, they set up an array in the Hornsby Valley. I think it's somewhere between Sydney and Wollongong, up in the hills, and basically it's just a set of where's that mouse? It's just a set of, please look at the screen, just a set of dipoles on posts strung above the ground with a reflector, which is basically looking upwards, and it could be phased to look at different directions, north-south, but they were usually phased to look vertically upwards. That way, as the Earth rotated, they did a scan of the sky. And all they did was collect the records on a chart recorder. They used a fancy diode amplifier called a square law detector, so the voltage out was proportional to the power in rather than the voltage. And they put it in the chart recorder. And Alex Shain is probably the first recorded case of someone recording the signals from Jupiter. But they thought they were interference, which I think I would too. They didn't occur at the same every night. Some nights they were there, some nights they weren't. So this is a bit like Alice in Wonderland, and if you remember, I think there was the Red Queen when Alice said something was impossible, And the Red Queen says, I try and believe at least 3 impossible things every morning before breakfast. Well, radio astronomy is a bit like this, especially when you start looking at the planets. Planets don't emit radio signals, and the stars emit just a hiss. Planets don't emit signals like this. That's one of those impossible things. Well, it wasn't until 1955 when Burke and Franklin were testing a Mills Cross array for the Carnegie Institute in Washington. It was somewhere in some daring country out in Maryland. And a Mills Cross, for those you don't know, is basically 2 interferometers with a north-south arm and an east-west arm. And the north-south arm gives you a beam that's narrow in the east-west direction and wide in the north-south. The north-south arm gives you the other way round. And if you combine the two together, and any source that's in both beams simultaneously is on the, it gives you a beam that's a couple of degrees, about 1.5 degrees wide, got a few side lobes, and the same thing, you phase up the east-west, look straight up, you phase the north-south for the declination you want to go, and as the Earth goes around, it sweeps up. And they discovered the same thing. They were expecting, for the interferometer, which is used to get the sharp lobes, you expect a signal that looks like that. But what they got was this bloody ratty old thing, and half the peaks missing. And I think the joke was, it was about 3 o'clock in the morning the first time they heard it. Bloody cowhand off to milk the cows. He said put a suppressor on his ignition. But it kept coming back and coming back, and it got about 4 minutes earlier every day. That means it's moving and it's fixed in the stars. But it didn't quite move 4 minutes every day, because they actually observed for 4 months they were doing all this work. It moved 20 minutes closer to the Crab Nebula, which is the source they were trying to use to calibrate the array, and then it moved back again. So what is it that wanders around the sky? It's called a planet. And one of the nights they were hearing it, one of them, I think it was Franklin, walked out. It was a lovely clear night. He looked up along the beam, and there's Jupiter shining. Well, they thought, before we announce we've seen radio signals from Jupiter, we'd make sure we get our facts straight. This was 1955. People were seeing flying saucers everywhere. There were fears of Russian missiles, and it could sink your career rather rapidly, like claiming cold fusion many years ago. But they looked up, and lo and behold, every time they heard the signals, Jupiter's right in the middle of their beam. And Jupiter went down. The other planet that was in the area was Uranus, but since Uranus is further out, it doesn't have the retrograde motion as Jupiter. And the reason planets seem to move backwards, is that when the Earth is on the same side as the planet, it's in conjunction, it's travelling faster than the planet because it's closer into the sun. So if you look out at the window of a car and you're going passing it, it looks like it's going backwards. And so compared to the stars, it looks like it moves backwards to the stars. And here, if I can get the mouse to work properly, if you look at this as probably taken from the Hubble Space Telescope up in the northern hemisphere, you can see Jupiter moving down, and then as it gets toward the same, the Earth moves the end of its orbit, gets the same side as Jupiter, gets brighter, because here it's only 600 million kilometres away rather than 900, and then as the Earth gets the other end of its orbit, Jupiter appears to move quickly down, and then later on it does another loop, and it does 11 such loops around before it eventually gets back to where it was. And the other thing that something went funny here. I don't know, maybe. Burke and Franklin got all the data from Shain and Alex Shain, and also the University of Florida in the late 50s was also said it had a decametric radio astronomy, and they discovered that the chances of observing one dropped dramatically with your frequency, and once you got to about 30 megs, they were very, very, very rare. And there are two sorts of bursts. That's the long ones, but there was also the short burst. That's it.
Just get that. Yeah.
Sorry?
Right click on it, I think.
Oh, okay. That's what the long bursts sound like. But I just want to try and get this other one. It should, if I can get the mouse on it and double click or something. Where's that? Ah, there it is. No. Anyway, it sounds a popping sound.
Okay.
Now pop, 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 pop. And they sound like ignition interference, very much like ignition interference. Well, what they also discovered is that it wasn't there all the time. Seems all the formatting's gone funny in the from different screen pixel size or something it could be. But if you look at Jupiter, now that should Jupiter should rotate. There we are. That's actually a time-lapse picture of Jupiter taken from the Hubble Space Telescope, and the pictures are taken 9 hours and 55 minutes apart. And what you will notice, or you should be continuously doing, is that the equator, the clouds are whipping round in 9 hours and 50 minutes. In the mid-area it's about 9 hours 55, a bit longer. And things like the Great Red Spot, which is a storm, it's as big as the Earth, a storm that's been observed since Galileo first observed it. It's been there for the last 400 years. And if you watch the motion, see the clouds going round, Jupiter is incredibly turbulent atmosphere. And no one actually knew the rotation period of Jupiter. So they used to use, for astronomers, they said have two sets of longitudes on Jupiter. A system 1 based on the equator, and a system 2 based on the mid-latitudes. And originally Burke and Franklin thought, well, if we're listening to thunderstorms on Jupiter, then they must, and they're not there all the time, they must relate to some sort of surface feature. Well, or cloud feature anyway. So they looked at the Great Red Spot, but they tried at taking the 7 years of data they had to see whether it correlated with the red spot. Well, what happened is that it didn't quite. But if they dropped the orbital period by 14 seconds, they all lined up. So that's actually looks like that was the rotational period of the core of Jupiter. And the other thing that Burke and Franklin did, which was rather innovative, they actually set up a small array of cross dipoles and discovered it was circularly polarised. Whereas normal radio stars are completely unpolarised. And they also discovered that the main source here was right-hand circular, this one was left-hand circular. And the short bursts, the pops, they occurred more on the early source. Bit of a giveaway. It's coming from a magnetic field. What? Jupiter's got a magnetic field? Another impossible thing to believe before breakfast. And of course, for a bit of revision, when a charged particle hits a magnetic field, it likes to go round and round in circles like a dog chasing its own tail. And the frequency, called the cyclotron frequency, it depends on the charge and the mass. And for electrons, it's 2.8 megahertz per Gauss, or 28 gigahertz per Tesla, and a Tesla is about the magnetic field you get in an MRI machine. And a Gauss is a bit more sort of the Earth's field's about 0.6 of a Gauss at the poles. And the other thing with magnetic particles, they don't like going across a magnetic field. So when they come into a magnetic field, they spiral down. And as the magnetic field gets more and stronger, the pitch angle goes to zero, then they reflect. And so, like on the Earth, all the electrons and protons coming out of the sun get trapped in the magnetic field and form radiation belts. It's like a giant magnetic bottle. And when you get a storm and the bottle gets a squeeze, you get it dumped into the ionosphere and you get an aurora. So if you look at the output different frequencies, you notice in the first quarter of Jupiter's rotation you get virtually nothing. And as the frequencies go up, the two sources tend to become more differentiated, And once you get above about 25 megs, you only get the early source. Now the other so by the 1960s, once they'd worked this out, the old chart recorders aren't going to work properly. So in the BC area, before computers, the sweeping receiver became the standard method of looking at Jupiter, especially the long bursts. And basically, it's just a receiver that tunes from about 10 megahertz up to about 40, and some of the early ones used to have a motor driving the tuning capacitor, which would also generate a voltage to give a frequency information. And so they'd have a filter about 100 kilohertz wide. They'd rectify it, they'd put it onto the control grid of a cathode ray tube and modulate the intensity of the beam, and the frequency control went on the y-axis, and that gave you a vertical line on your oscilloscope that was intensity modulated. They put a 35mm camera in here with about 50 foot of film and a motor that slowly wound it across, and it gave you a display like this up here. And this is some typical L-burst spectra. In the 1960s, the really active area in Jupiter work was the University of Colorado in Boulder, and the big cheese was a fellow called Jim Warwick. And if you look at these spectra, you'll notice that on the main source you occasionally get a 25 meg signal, but mainly get very few signals above 22 megahertz. That means if it's coming from a magnetic field, the magnetic field at the pole there must be about 8 Gauss, which is about 15 times the Earth's magnetic field. But if you look at the early source, they go up sometimes up to 35 megs. They're pretty rare up there, which means you've got a field of around about 12.5 Gauss. So the magnetic field of Jupiter is somewhere about 20 times as strong as Earth. It's really quite a strong magnetic field. Now, we thought Earth had a magnetic field because it has an iron. We think it's got an iron core. We don't really know. No one's ever had a sample of it. We're only working on seismic evidence. But because of its rotation, and it's obviously some differential rotation because the planet's drift around and all that sort of stuff, it's got a magnetic core. But it's the only one of the rocky planets that does have a magnetic field. But it turns out Jupiter's got a very strong magnetic field. And the other surprising thing is that, of course, if you look at Jupiter, and I've said you've seen Jupiter through a pair of binoculars, you see the 4 Galilean moons. There is a fifth one, Amalthea, which is very small and it's in quite close to Jupiter, and it's shaped like a potato and quite dark. You need a telescope to see it, and you've got to have exactly the right time. But Io, the first moon Io here, is about the same size as our moon, virtually the same distance out. It's 420,000 kilometres out, which is just about 5% bigger than our moon. But it rotates every 42 hours because Jupiter's got a pretty amazing gravitational attraction. In fact, Jupiter is the bully of the solar system. Anything that gets too close to Jupiter either gets captured, broken up, or flung into space. They use that to get the probes out to the outer planets, get them close to Jupiter and pick up the energy out of the gravity, out of its orbital motion. Now, these are the pictures of the moons. Io is the one we're interested in, and it's funny. It's got a funny colour to it, and there's a reason for that I'll explain later. Europa's of interest. It's a bit smaller. It's about 600 odd K out, 1,000 K out, and they think it's covered in ice and it might have a liquid ocean underneath because it's being warmed up by the gravitational tidal stresses. Ganymede and Callisto. Ganymede's actually bigger than Mercury. It's a very large object. It's probably been captured at some stage, and Callisto about 2 million kilometres out. But there's about probably another 60 odd moons as well that we know about. And of course now the Galileo and the Juno have been out there, we've discovered an awful lot more. But this is 50 years ago. We really didn't know much about the outer planets, only what you could see through a telescope from the Earth. Now, the other impossible thing that you've got to believe, we've got up to 3 already, haven't we? Yep, we might have to do worse than the Red Queen, is that if you look at the longitude of Jupiter on here and the probability of seeing an emission, and you look at 20 megahertz, and you look at the phase of Io coming from superior geocentric conjunction, which is a fancy word for saying behind Jupiter relative to the Earth. When it gets around in this area, you get your emissions. Now, how can this moon, almost 500,000 kilometres out from Jupiter, control these short radio bursts? Well, that was the question, and by 1970 that was the real question people were wondering about. They'd worked out roughly from the data that Jupiter, the other information, CSIRO did some microwave work on Jupiter, and at 2.3 gigs you can see the thermal radiation from the surface, because Jupiter's actually warmer than you expect. It actually dissipates more heat than it gets from the sun. People are still trying to work that one out. It was almost big enough to be a star, but not quite. And this is the radiation on the sides from the radiation fields. And if you go down to 1.36 gigs, then you don't get much. It's further down the thermal tail, but you can see the radiation, synchrotron radiation from the radiation belts. Now, so by 1970, they worked out that Jupiter does have radiation belts like the Earth. It has a magnetic field about 20 times as stronger. It's offset. It's actually the opposite polarity of the Earth's field. The North Pole points north, but the Earth's field's the other way around, because your North Pole of your magnet is looking north. So the North Pole in the Earth is actually south. And it's also, the sources are not 180 degrees apart, so it's actually displaced from the axis a bit. That's what worked out from the radio waves. So it's not only a bit south, it's off a bit. It's all a bit strange. But so they think the old bursts are basically due to electrons. As the planet rotates, this part on the left here is coming towards the sun. The sun's actually blowing solar wind. It's compressing the plasma coming out from the sun is hitting the magnetic field, and it's giving it a squeeze. And so as it comes around, it's squeezing it down. And now at the low frequencies, around about 5-10 megs, it's coming from fairly high up. So really, it doesn't matter what the rotation of the planet's there, you're going to see it. But at the high frequencies, unless you're looking at one of the poles, it's going to be hidden by the planet. That's the very hand waving. That's my story, and I'm going to stick to it, because I know hopefully no one here knows any better. You know, I'm not going to spoil a good yarn by keeping to the facts. This was 50 years ago, and I can claim it dementia if it isn't true. But then again, what about the S-bursts? It's a bit like the old days of the political meeting. What about the workers? Yeah, what about the S-bursts? Well, by 1970, they knew the S-bursts had a duration of a few milliseconds. No one had managed to record them. They had bandwidths less than about 250 kilohertz. They were narrow band, not broadband like basically broadband noise like the L-bursts. And the way they knew that is people had done a few experiments with 3 or 4 receivers about 300 or 400 kilohertz apart, about 100 kilohertz wide, and when these burst, they'd watch the little pips go down. So they didn't all go off at once, but they saw them go off in sequence. So yes, they had a very rapid negative frequency drift, and the signals were quite strong. These were several megawatts being emitted from Jupiter. This wasn't a little chap with a spark coil on Jupiter. But of course the scanning receiver, which scans, say in this case, if he's looking for 16 to 20 megs, and if it scanned that every second, these bursts only last a few milliseconds, so you might get a pip, but no, only one sweep will ever hit a burst, so there's no way of working out the spectral information. What you need to do is somehow fill in that frequency time signal so you actually get all the information. Well, it turns out that in 1956, who remembers 1956? Some people here do. The Olympic Games came to Melbourne in 1956. Television arrived in Australia in 1956, so the people in Sydney could watch the games from Melbourne. They'd fly the newsreels up and show them. And I remember going to a shop in Sydney once in about 1958 and gawking at a television set in a shop window. But Ampex developed the first video recorder, and it had a spinning drum with 4 heads on. It painted 1,000 lines a second on a 2-inch wide videotape, which was moving at 15 inches a second, which was the speed for hi-fi audio recording in those days. On the top of the track they had an audio track, and on the bottom they had the sync pulses to synchronise the head. And at $45,000 you could buy about 5 houses for that in those days. Bit beyond the research budget of most universities. But in 1969 Philips came up with the first attempt to get into the domestic videotape recording. This was before colour television. It was black and white. It had a 3 meg bandwidth, and it was just 3 meg bandwidth. That was enthusiastic, but it had a drum with 2 heads on, which ran at 1500 revs a minute. So each head wrote 20 milliseconds, or 1 field of an analog television signal per track. As it went up the track, they had an audio track on one side and a sync track on the other for replay. And I think the tape used half-inch tape, and it ran about 15 inches per second, and each reel would last about 40 minutes, and they were available for $500 in New Zealand and Australia. Well, it turns out that Dick Dowden, who had been, or Richard Lindsay Dowden, I'm sorry, is a full name, he'd been made the junior professor of physics at the University of Otago in 1968. And he did his PhD here in Hobart with Bill Ellis. I always knew him as Bill. I know his name was Graham, I don't know. But everyone in the trade called him Bill for some reason or other. And Dick was a real lateral thinker. And this thing came along, and Dick thought about it, and he thought, he wrote a letter to Bill and said, Bill, I think I wouldn't know how you can see resolve these S-bursts. Why don't you make your receiver and convert your RF, 3 megs of RF into 3 meg video signal, record it, then you can play it back in the freeze frame mode. It'll go round and round and round and round and round and play the same bit, and you can play it 200 or 300 times, and then quietly sweep a filter up here, and you'll get all the spectral information. And a few months later, Bill wrote back to Dick and said, thanks for that, Dick. He said, I've spoken to the university. I managed to persuade the university to give me about $5,000 to buy a couple of these and take on a PhD student. I'm going to have a go. And Dick thought, maybe I should have a go too. And that's where I came into the picture, because I was looking to go to the University of Adelaide, but the University of Adelaide had run out of money, and I'd written some letters off, and one of them was to the Professor of Physics at the University of Otago, and I got a letter back saying, I do have a project looking at Jupiter's radio signals and a grant. Are you interested? And I said, yes, please. So on the Ides of March 1971, I took a plane from Melbourne to Christchurch, and the following day took the train down to Dunedin. And now Bill had got a bit of a jump on us because he already had a radio telescope set up, and he had a department which actually was experienced in building radio receivers. I was it. But for those but essentially, the 1970, the early 70s was an ideal time. Jupiter was in the southern sky. It was from 1971 to the beginning of 1974. It was between 21 and 23 degrees declination. It was too far south to be observed by people in Boulder. But Hobart and Dunedin were in a good position to see it. And in 72, 73, Jupiter came to opposition, was in opposition right in the middle of winter, so you got a really long, it would be in the beam right in the best time, observing time, from about 11 o'clock at night to about 3 o'clock next morning. And so in 1970, Bill, I think, started late 70, and I started in March 71. There were 2 projects started. In 1970, now Ellis and McCulloch, I don't know I think it might have been a Brian or a Ben McCulloch. If anyone knows his first name, I don't. I never had any dealings with it. I wrote to Bill, had correspondence with Bill Ellis, and he gave us a bit of it. He'd actually he'd done some of the design on the spectral analysis work, so I got a bit of help out of the University of Tasmania. But Basically, there's Jupiter in the southern hemisphere. Boulder's up here in the blue line. It's 60 degrees, it's only 30 degrees above the horizon. Whereas here's Hobart at 42.5 degrees south and Dunedin at 46 degrees south. Now, the other interesting thing in the early 70s is there was the grand alignment. All the outer planets were aligned such, and it only happens about every 150 years, where if you shot a rocket up, and the rockets, even the rockets that went to the moon, could only get a probe as far as Mars. They just didn't have the power to get any further. But if you put the rocket just behind Mars, then it would pick up about another 10 kilometres a second off Mars and fling it towards Jupiter. And then it would get Jupiter and fling it off towards Saturn, then Uranus and Neptune. But there was this one window. They had to be launched sometime in the 70s for this to happen. Otherwise, they had to wait a long time or get better rockets. So it was really a good time to be doing it. Now, for those of you who wonder where Otago is, it's actually about the bottom third of the South Island of New Zealand, and the name comes from Otakau, which is red ochre, Maori for red ochre, because the few Maoris that got down that far used to trade red ochre. It was a valuable supply. And Dunedin was a bit of a miserable old place, and for the climate, as the Scots said, a good place to be dour. And the joke was that it was settled by the Presbyterian Church as a place away from the corrupting influences of the English. But they'd forgotten that God has a sense of humour. He'd filled the rivers with gold, and lots and lots and lots of it. And by the 1880s, Dunedin was the largest and the richest city in New Zealand, and was the financial hub of the country. And it has the oldest, and the founding fathers actually set up a university model on Edinburgh, and the only medical school in the country for 100 years. So and this is the main building of the university, and the physics department is on this end of it here, and there used to be an 80-metre aerial strung from there to the top. It was originally used for some of the early broadcasting experiments by Prof Jack in the 20s, but I had a room up in the top there, and we did pull it down and replace it with a balanced dipole for getting good time signals for the VLF work, which was in this little annex here, the observatory observing work. And when we didn't need it for that, I used to plug it into a transceiver. I had the flasher shack in New Zealand. And the field station was a place called Swampy Summit. Now, flatland in Dunedin is a bit like trying to find rocking horse manure in the Simpson Desert. If you think Hobart's hilly, go to Dunedin. The nearest flat land is the airport is something like 40 kilometres out here down in the Tiree Plain. That's the first place. So Swampy Summit here is a hill about 4 kilometres long and 2 kilometres wide. And on the southern end was the transmitting station, VHF transmitting station for the air traffic control for Dunedin Airport. Out on here was the microwave station that provided the links for the telephone up to Christchurch and down to Invercargill. And up on the northern end here, there was the receiving station. It's about 3 kilometres from the transmitter for the air services, air traffic control. And about 200 metres away from that was the university had a field station, and around here were several loops, and they did VLF measurements, did VLF signals. And the nice thing about Swampy Summit was that it had steep sides and an almost flat top, had a slight. It was a peat swamp, and if you want an electrically quiet spot, try a peat swamp. It's a beautiful conductor, and it shielded it from all the electric radiation. It was a beautiful electrically quiet spot. At about 400 metres north of there was a slope 40 degrees facing due north. And what was the advantage of that? And we built an array on that. And why put an array on a 40-degree slope? Because the Earth's axis, if you looked at the stars, the south celestial pole was 46 degrees above the horizon. The axis of the area was 40 degrees above the horizon, and so as Jupiter, which is this green dotted line, rose and set, if you put a collinear array and phase it up to look about 23 degrees off the axis, for the next 3 to 4 years, Whenever Jupiter was above the horizon, it would be in the beam. You did not need to steer the beam. If I'd put a horizontal aerial, if I could have found a bit of flat land to do it, you'd have only got an observing window of about 3 hours a night. This gave me 6 to 7 hours a night when Jupiter was in the beam. So, if you've ever tried building an air on a 40-degree slope, that's what it looks like. And everything had to be carried up and down, and we soldered things with a scope soldering iron and a 6-volt battery, and they will solder 7044 hard-drawn copper, sweat it in the middle of a sleet. That's how much heat they'll generate. And that's the aerial. The poles are just half a length of 2-inch PVC water pipe. You can possibly see the insulators there. They were two wires 600mm apart to make it nice and broad band, and there was a number 8 fencing wire that's everywhere in New Zealand, number 8 gauge fencing wire that held them all together, because it is on a slope like that, well and truly anchored, and they were held up with poly pipe and star pickets driven in the end to hold them. And they were each, at this point here, there on the pole there was a toroidal balun, 75 ohm coax up to a phasing box there, and then a preamp and 400 metres of coax back to the field station.
This was obviously done in summer, Mike.
No, that was done in the summer, yes, this was 1971. Oh yes, up there in the winter it was I spent 2 years up there most winters nights, going up there about 8 o'clock at night and coming down about 8 o'clock in the morning. Yes, and I managed to produce another couple of kids in the meantime. But we had a 10-element collinear array, a preamp, and because we didn't have much of a television electronics department, we decided to avoid trying to design a broadband receiver from scratch. We bought a cheap transistorised television set. They've got a 5 meg wide AF, haven't they? They're reasonably flat. So I pulled out the turret tuner, fed the signal straight into the IF, used a 60 meg local oscillator. And at the other end I put a 35 meg injection oscillator and put a product detector in instead of the diode, and put a buffer on. Now that would generate 0 to 5 megs of video, but with the recorder would only do 3. Fed that the video recorder. We also had a detector to look at the level, the RF level on a chart recorder. You had to have a chart recorder to be a proper radio telescope. Had a spectrum analyzer, had a recording oscilloscope, and of course, with the good old Scottish tradition, we couldn't waste the screen on the television set, so I rotated the deflection yoke 90 degrees, so it was scanning at 50 hertz in the horizontal direction, which was the frequency display, and the line display was coupled to the output of the spectrum analyzer, so you got a panographic display. No waterfall displays in those days, and an audio monitor could see what they sounded like. And that's what it looked like. Sorry about all the... oh, it looks all right. It looks terrible on here. Oh, it looks all right. Oh, not really. But there's your recording oscilloscope up there. That's the camera and the roll of film. That was the box of electronics. The front end was there, and the rest of it was the things generating the sweeps. There's the television receiver. You can see the IF cable going in there, and you can actually... I had a calibration signal, so you can see the 0 and the calibration signal on the display. There's the video recorder, and because this station was unheated, because we borrowed the power from the civil aviation about 200 yards away, so we were limited to about 10 amps draw on 230 volts, so didn't really run to heaters. It was only designed to run tape recorders and clocks and that. So I spent a couple of years up there with 2 pairs of socks on, long johns, and drinking lots of tea made with a spirit burner, because of course you couldn't run an electric jug. But this is a display of an L burst on the spectrum analyzer. The time markers were actually a unijunction transistor running at about 100 kilohertz, which put a nice spike, ran for a few milliseconds, and that's the actual midnight. That was 12 hours GMT, which in New Zealand of course is 12 hours ahead of Greenwich. And to analyse the tapes, we invented a thing we called the Zenograph from Zeus. Got to use the Greek root just to sound superior. Couldn't have called it a Jovigraph. And essentially the videotape recorder, the video signal we put into a swept filter from 0 to 3 megs. I had to build that. That was pretty simple, just basically a receiver that went from 0 to 3 megs. The output of that we put through just a AM detector. The tuning, the sync pulses coming out of the head. It turned out I had a lot of trouble synchronising the videotape, so I just let it free run. It ran at about 49.5 frames a second rather than 50. It was designed to run a fraction slower, and then the sync pulses locked in. It's a bit like a multivibrator. You run them a bit slow and then trigger them, but I had trouble triggering them, so in the end I realised after I started to analyse they hadn't synchronised, but it was close enough. As long as I could lock the analyser onto the thing, it was fine. And had a crow, so the 50 hertz swept across the field. The slow sweep was about 3 seconds, went up the field, and it was intensity modulated. And this is what it looked like on the screen. Now, we actually analysed 5 lines of data on the same screen. What we did was just put a DC offset on the horizontal sweep. So it would sweep up there in frequency, then the trace would move across, sweep there, sweep there, sweep there, sweep there, and at the end of the 5, the shutter would shut, the camera would move on 1 frame. And it usually carried 50 foot of film in the camera. It was just fairly standard, probably cheap 35mm black and white film, probably not even film quality. It was just for recording oscilloscopes. Camera recording was very, very common in those times, because there was no, recording that sort of information on mag tape wasn't easy, and film was readily available. Kodak hadn't gone bust at that stage. That's what they sound like, and they're slowed down like. University of Florida had these on their website. That's what the chest burst sound, slowed down by a factor of 128 times. Now, right, this is the data that Bill got, and you can see each of those stripes is 20 milli. You can see the S burst being resolved, and he was running from 12 to 15 megs. And about 6 months later, this is the data I got, but Bill was positively brightening the trace up with the signal, and we were blanking it off. It tends to suppress the noise a bit better, because film can add but it can't subtract. And so these are the first ever spectra of the Jupiter S-burst ever produced. Now Bill shot a letter off to Nature to say that he'd got it, to get bragging rights. That's fairly important if you want to claim something. And about 6 months later, Dick and I shot a letter off to Nature saying yes, we'd also seen them, and confirming that Bill's results were genuine. It's really good if someone else can back you up. And so I was running it. Bill was running between 12 and 15, and I was running from 22 to 25. But that was important because there's no point in both of us doing it at the same frequency. We wanted a different frequency so we could get information for analysing it, what was happening. So what on earth is causing them? It's obviously different process than the long bursts, which seem to be stuff being precipitated down from the radiation fields into the upper atmosphere. This seems to be coming from the outer radiation, but from the outer part of the magnetosphere. Now Bill came up with the idea that Jupiter's rotating around here. Jupiter's rotating for 10 hours. Io takes 42 hours to do an orbit. Now the magnetic field and all the charged particles are whizzing round every 10 hours. So the whizzing past the magnetic field here is whizzing past Io at about 50 odd kilometres a second. Now Io is 4,000 kilometres across, and if it's a conductor, there's going to be one hell of a voltage generated across there. It's a conductor going across a magnetic field at very high speed. And the argument is that electrons can flow along the magnetic field lines, they can't flow across them. So a magnetic field line in plasma acts like a wire. So the theory was that this would be causing electrons to come down towards Io, flow up and come back, and that would cause electrons to be injected out of the ionosphere into the magnetic field lines. And and if they're coming up, they're going to be decreasing in frequency because the field is so that near the pole they're going to be whizzing around at high speed. As they get up, they're going to be slowing down, and that went down a bit like a lead balloon over in Boulder. They said, no, but Io is just like the moon, it can't conduct electricity. Another thing, impossible thing you have to believe. Well, it turns out that these are the data that Bill got, his slopes, and he worked out this green line is what he reckoned the slope should be against the frequency of the emissions against the steepness of the slope, and this was the data we got in Dunedin up in the high frequencies, and so it seemed to work. Okay, it needed a bit of work on it, but the concept of Io being a short-circuiting the field seemed to work. Now, the icing on the cake was that in November 1973, the very, very first probe went past Jupiter, Pioneer 10, and it came in behind Jupiter, in between Jupiter and Io, and got flung out towards Saturn. It carried an electric and a magnetic field detection. It didn't have any cameras in. They just didn't have the bandwidth on the transmitters in those days. But it also, I think, had a UV detector, and it detected an ionosphere on Io. If you've got an ionosphere, you can have conduction. So that's the third impossible thing you've got to believe. Now in 1974, Pioneer 11 went past, and the thing is, Pioneer's 10 data was published in 1974, so it was published in time for me to put in the thesis. And it actually said, yes, Jupiter does have this sort of magnetic field, and it's about the same strength, and yes, there's a lot of radiation in that field because there was so much that it actually corrupted one of the memories in Pioneer 10. And they frantically, before they launched the Voyager spacecraft, put extra shielding around the memories so they didn't get corrupted. They had to reprogram one of the experiments after it left Jupiter, which is a pretty slow process when it takes about 20 minutes for the signals to get there and back, and you've got data rates of only maybe a few kilobaud if you're lucky. But the other thing is that Voyager 2, when it went past, of course Voyager had lots of had cameras on it, it actually detected a volcanic eruption on Io. And the spectral analysis indicates that there was a lot of sulphur in it. So the brown-yellow colour on Io is probably sulphur. And so what we now know about Jupiter, and initially from the radio data, is that Jupiter has a very large magnetosphere. It's got very intense ionisation belts. In fact, if you were in a spacecraft here, you'd probably get a fatal dose of radiation in about 2 days. It's that sort of, and are very energetic particles. The fact they emit synchrotron radiation up in the microwave range indicates they're pretty energetic. Well, that's not surprising when you think of the energy being generated by the rapid rotation. And there is definitely very large currents flowing up and down the flux tube through Io, because the one thing they didn't have in the 1970s was the Hubble Space Telescope. Amazing thing, Hubble. And this is a photograph taken of Jupiter at ultraviolet wavelengths, because Jupiter's mainly a hydrogen atmosphere and hydrogen fluoresces in the ultraviolet. And if you look, you can see the aurora, and you can see they're both on the same side of the planet. It's a bit kinky, but it's, it's offset. But when the planet's the wrong way around, you can't see any magnetic pole. And this is one taken of Io, and this is actually the north pole of Io and the south pole of Io. So you can see this current flowing across Io. And if you look, this didn't come from the Hubble. I'd say this came from the Galileo space, the orbiter that was around Jupiter for 12 years, taking lots of pictures. This is ultraviolet of the northern aurora. And you can see this is the flux tube going up through Io, and you can see there's an incredibly intense current flowing up there. This hot spot, and you can see whereas the planet's rotated, you can see the residual ionisation in it. And there's a small one from Europa and a small one from Ganymede. So, yes, all those impossible things turned out to be true. So I'm just wondering if I find the Mount Hatter soon. And of course, we now know that what we knew back in 1970 about Jupiter was really, you could have written on the back of a couple of postage stamps, compared to what we know now. And the Galileo Explorer spent 12 years in orbit, and I think it did something like about 80 orbits, so very eccentric orbits, so to come in close to Jupiter, then go out and go around one of the Galilean moons, so it picked up an awful lot of information. And they deorbited that in 2003, because what kills space probes is that they have gas on them to do minor orbit corrections, so they'll do minor orbit corrections to make them go to do various missions, and eventually they run out of gas. So usually what they do, then these things carried a great load of polonium in the back to generate heat to run the power generator. And so what they did, rather than run the risk of contaminating Callisto or something like Europa, which they thought, may possibly have some sort of life on it, is that when it comes in for its final orbit, they let all the gas go, put the brakes on, and it burns up in the atmosphere and gives a lot of information about the pressures and temperatures in the atmosphere. Good kamikaze probe. And these days there's Juno, which is solar powered. I believe each of these arms is about 100 metres long, and that went into took 5 years to get there, but it went into orbit in 2016, and it's due to go till 2025. I think it was due to go till about 2000 later this year, but they've extended the orbit by another 4 years. They reckon it's going to have enough gas to keep going, and that'll be deorbited and sent into Jupiter when it runs out of gas in its propulsion. And that's about where I'll stop. Actually, I've got through a bit quicker than I expected. So essentially, that information it's a bit out of date, but essentially that's how I played a very, very, very small part. The Kiwis gave me the money to go over and do it, so I can't complain. The Kiwis were very good to me. They gave me a couple of extra kids as well, so...
Questions for Mike?
Yeah.
Yeah, I've got one.
Yes.
What you were doing,
Yes.
was Groth Reaver trying to do the same thing?
I don't know what Groth Reaver was doing then. I think he'd become a bit of a recluse by then. He was up in. He kept wanting to look lower and lower, down around 3 or 4 or 5 megs.
Yeah, 'cause
That's
you're
why I went up
massive
and built these enormous arrays up around Bothwell.
Yeah, I've been up there for a while.
Yeah. As far as I know, he wasn't looking at them. This idea of using a video recorder was, I think Dick Dowden came up with it originally, and he suggested it to Bill, and Bill said, "Yeah, that sounds like a good idea. I'll try that." And Dick says, "Oh shit, I think I'll have a go too." And so we decided that we'd run at different frequencies. If I'd have realised how infrequent, I got my PhD on one really good storm. If I'd have realised the odds of failure, I'd have gone and looked at something a little more chance of success, like multiple birth thylacines in Russia or something like that. Don't ever do a PhD on observational physics on a transient phenomenon. The gods must have conspired to decide to do it. So instead of being a bullshit collector, I'm now piled higher and deeper.
Now, Mills Cross
Yes.
receivers, there was something in Sydney, like out in Western Sydney.
Yeah.
It was some sort of a crossed antenna array. Do you know anything about that? Because I think it's all gone now.
No.
Mike doesn't, but Warren does because he worked on it.
Yeah, I think Bernard Mills built his first full-on cross up near Badgerys Creek, which I think has gone. But I'm not sure when he would have built that. Probably
52, I think.
52.
Yes, 52, 53. Yeah, it was 96 elements, I think.
And so it was an unusual concept, but fairly groundbreaking, that caught the attention of Harry Messel then at the University of Sydney,
Yep.
and offered Bernard Mills then to build him the 1 mile cross. So it was a
Yep. Yeah, they
configuration
did
of-
build some enormous ones out there. I think that's where the new Sydney Airport's being built.
Yeah, well, that was the Badgerys Creek.
Yeah,
And then the Mills, the 1 mile cross was then built near Bungendore, which is not too far from Canberra.
yeah.
And that's still operating today.
Okay, and is the Colgura radio heliograph, solar heliograph still working? The radio heliograph?
Don't know.
No,
don't know about
that
one.
was up 3 kilometres in diameter, that one, I think about 90. That was a big thing back in the late 60s. I remember Paul Wilde giving us a couple of talks on it, and he was director of radio physics in those days. Yeah.
Yeah, so the earlier days with Bernard Mills was, I think, with the Department of Radio Physics, the CSIRO, and then he moved to be professor at the School of Physics, the Astrophysics Department at Sydney University.
Yeah. Now, Sydney was a major source of work in the early days of, especially the lower end of the radio astronomy. They were major moves to take us. Sydney, Cambridge, and Hobart was another major centre. The Americans were quite late getting into the game, actually, by comparison. But no, Australia was very well up there, and yeah, the Jupiter signals. Well, Shain was probably the first, one of the first people to record it, but it didn't sound like, it wasn't what you were expecting. It come on with so many other many things. I've always seen them for years. Is that what they are? And there was one more slide that, if who's into conspiracy theories?
Oh, yeah. Oh, we love them.
One night I had to go through lots and lots of, 35mm film with a magnifier. And one day, and I used to get these little hooked, occasionally these little hooked emissions. They looked a bit like a lambda. And then I noticed that all the dots made it look like a P. And I thought, oh, they're telling me to piss off. So I can always say, oh, you talk about DX, I got some DX from 600 million kilometres away. I thought, I saw that, and I thought, I'll just have, I cut that little bit of film off, and I took it over to Dave Lloyd, and I said, can you take me a print of this for with some of the stuff, and it's been, I found it when I was writing a talk in my, dug up through all my old papers, and found this among the print of this among the bits. So, yeah. So that's the question: do Jovians speak Greek?
You talked about micro VLF antennas up on Swampy.
Yeah.
What were they using the VLF antennas for?
They were listening for whistlers,
Oh, okay.
and all they were was a. I was going to talk about that tonight, but otherwise the talk would have been 2 hours long. I'll give a talk on that sort of stuff later about emissions from the Earth's magnetosphere. The Earth does talk to us. It's just that you've got to know where to listen. But yes, all they were was a 20-foot piece of pole, and four polycores up, and they'd put two loops at right angles to each other of the old 2-core lighting cable, the stuff you used to put in your roof to run the lights before they would insist on putting an earthing loop in them, and they just run that back along the swamp, put it through a transformer and into a decent amplifier and into a tape recorder, and then they'd record for about 5 minutes every hour. All around the world they'd record these things, and then they go back and put them through a tape recorder that had things that the manufacturer certainly wouldn't have ever approved of, where they'd play the same bit of tape, and they had springs. It was a bit like a cross between a tape recorder and a movie projector, where the tape went through in jerks but moved slowly, so they played each bit of tape about 300 times and looked at different frequencies all the time, and that's what gave Dick the idea of the of using the video recorder. So it was the Australians did it, except 2 of them were in New Zealand. The Kiwis may beat us at rugby, but we beat them at the Jupiter signal.
Very good. Any further questions? Can we show our appreciation of